as I told you, we have two specific classes. The first class is the Boltzmann machine. This is a sort of dummy model, a sort of toy example, which helps us and everybody to understand better the model. But if you want to think about Boltzmann machine, it's essentially the linear version of energy model. So where the energy model is essentially formulated by the most simple version, which is the quadratic function. I'm going to show it in the next slide. So this guy is quite simple. It's just it got inspired by the Ising model in statistical physics. But the point here is that this one is not going to really do generation for us at the end of the day, because this is too simple to be able to capture the data properties. So the more essential one is a neural energy-based model. And a neural energy-based model simply means that the energy function is a complete deep neural network. And this is the one which we would like to train, but I'm going to keep this simple version as well, because this is going to help us understand many basic stuff. And I'm not going to give you too much examples in this part, because as I told you, the basic energy-based modeling is somehow not used anymore. So the things we study here are essentially those we need later to understand how diffusion models work, because diffusion models do pretty much the same thing as we do here. So let's start with the Boltzmann machine. So the Boltzmann machine, as I told you, a dummy example, the most simple case that you can think of. In this Boltzmann machine, in the most basic version, we deal with data which is binary. It means there is a vector, maybe very large vector, d-dimensional vector, but every single entry inside that is a binary. You can think of, for instance, MNIST image, which you have made it binary. Just do extreme quantization. Every pixel is either a complete dark or a complete light, right? So there is nothing in between. So you just show it with 1 bit, right? 1 bit MNIST is one example. So you have such data, and then what you want to do, you want to use energy-based modeling, so you essentially consider one energy model. And as I told you, the energy model is supposed to take the data and give you energy level. This is the simplest energy model you can think of. So we have weight W. This is one matrix. And this matrix is learnable. So it means the parameters inside this matrix, I can learn them. I can optimize them. Now, I am going to multiply W with X. So I'm going to get one vector out of this multiplication. And then I compute the inner product of this vector with X itself. You get the idea? So Wx is a vector. You compute the inner product with X. Now, what should be the dimension of W if X is of dimension D? If X is of dimension D, this is X, which is of dimension D, then how many columns should W have? Also D, because it wants to get multiplied with this guy, right? And then the output of this Wx is going to be as same dimension as the number of rows you have here. But you want to take this guy again and multiply it with X, inner product, right? So it should be the same dimension as X as well, right? So here it should be also D, right? So this is guy W, and this is D by D. Okay? Now, one thing that in the basic model we consider, we assume that the main diagonal here is 0 always. So we don't learn it. It's always set to be 0. It's masked. Why? This is coming from the graphical representation of the model. You assume that every single pixel is not impacting itself. It's just impacting the others. Okay? So we did the same thing when we were doing conditioning, right? So when you want to generate distribution of xi, you don't consider xi itself, right? Anyone else, correct? So this is the reason here. And we assume that this guy is symmetric, meaning that this part is exactly same as this part. Okay? So again, these weights are same as this guy, so they are also gone. The only part that we are going to learn is this part, right? So the only parameters that we are going to learn are the one which are on one triangle, right? Everybody's clear? So this is the model. I mean, why this comes out of, as I told you, physical intuition plus some experiments. But at the end of the day, this was the idea of defining model in this form. Now, one thing that you can see here is that obviously this is a very simple model. It just includes one linear layer, right? And if you want to think in terms of neural network, you can simply say that, okay, I have X, which is my data, and then I'm going to pass it through one linear layer, W, right? I multiply X with W is like passing through one linear operation, one linear layer. I'm going to get Y. Y is the first term inside the inner product, right? And what I'm going to do, I'm going to get X again and multiply it with Y, right? So Y multiplied with X, this is now giving me the energy, right? And this guy, even though it has this kind of skip connection in it, but still it has just one linear layer, right? So it's the most simple thing you can think of, right? And the whole thing inside this box is essentially your energy model, right? This is your energy model. This is what you want to train. Everybody's clear? Okay. So this is the Boltzmann model. So here I have a minus. I mean, it's not a big deal. You can drop it. I just kept it to be consistent with the literature. But if you drop it, nothing going to happen, right? So you're going to learn instead of W, minus W, right? Nothing going to happen. So that being said, now this one that you see here is what we call it fully visible Boltzmann machine. And by fully visible, it means that everything that I'm going to learn, or essentially every single pixel inside my image, if you want to think of my X to be an image, every single pixel is visible to me. There is no parameter, there is no part of data that I am assuming hidden to be. Okay? So can I think of that? Well, yes, we can think of that. And this is when we think of latent space. But we haven't yet talked about latent space. This is the thing that we start with the next section. So this is what we call it fully visible, because we assume everything is there. Simply speaking, we are going to estimate or learn the distribution of X, Px, and we see every sample that we see includes all the entries inside X, right? All the pixels are there. So can we think of hidden components of the model or data? Yes, we can think of, as I told you, latent representation of the data, which is hidden to us. And we're going to talk about it in more details next session. Okay? But right now here, I'm not going to include it because, I mean, you can do energy modeling with latent representation as well. But as I told you, it's not anymore a trend, so I'm not going to explain it anymore. You simply see it later that you can easily extend it to the latent space case as well. Now, Boltzmann machines in the basic form, when somebody says like a basic Boltzmann machine is essentially what I showed you in the previous slide, but you can have extensions of it as well. So for instance, instead of assuming X to be binary, you can think of X being a continuous variable, right? So every single entry, every single pixel that you have is not a binary anymore. It's a continuous number, which is the richest form of, pixel you could have, right? There is no quantization there. So you can think of it as well, but it's not hard. If you put it in the formula, you're going to see that in that case, it's essentially the Boltzmann distribution of this particular case is going to reduce to the Gaussian distribution. And this W matrix is going to be the covariance matrix that you have. Yeah? So essentially, you have one Gaussian distribution, multivariate Gaussian distribution, whose covariance matrix is learnable, right? That's it. Everybody's clear? Yeah? So you can do that, but people call it Gaussian Boltzmann machine. But again, this is too simple to do anything for us. So you can simply just have it in mind as a kind of example. Another thing is that I can go beyond binary. This is not a big extension, right? If I have a, I don't know, 4-level discrete variable, I can think of 2 binary variables, right? So it's not a big extension. And usually, again, people don't consider it because Boltzmann machine is not really practical. It's just a example. OK. Now, Any question on Boltzmann machine? So everything clear? So the energy model is the most basic one, which you can think of one linear layer involved, and then you want to train it. That's what fear. Now, another kind of model which is more serious is the neural energy-based model. And neural ones are essentially thinking of this whole, conversion of your input to the energy level as a neural network, right? So there is no need anymore to specify the data space, so you don't need to have binary sample entries inside your samples, general ones, so like the classical images we have, classical data that we have. And the other thing is that the energy model in this case, you cannot simply represent it with a simple linear layer or something. So it's probably a very deep neural network. So just thinking about what we had before, it was the Boltzmann machine. So this X is going to connect us to the energy level. Now we forget about everything. We put one very deep neural network here, which does this job for us. And essentially, we cannot, we can just, for example, backpropagate over the network, things like this, right? So this is the one which could essentially work in practice. And we're going to talk how we can train such a network as well. So, questions? No question. OK, great. So if you got no question, then let's start with looking at these energy-based models and see whether we can generate by them, like sample from them, and also how we can train them, right? Because if we have one model, if I fix one energy network, one energy model, then the thing that you want to do, you want to get a bunch of data samples, train it, and then sample from it, right? Train it to just fit it to the data distribution, and then sample from it to generate a new sample, right? This is what you want to do. One thing that you should keep in mind from now on is that when you are talking about energy-based models, you are specifying energy model, right? You're not specifying the distribution, correct? So you don't have any specific network which takes data and gives you back, takes sample and gives you back the distribution, right? You have something that takes sample and gives you back the energy level, right? And anything after that is on you. The Boltzmann formula is on you, right? Everybody's clear, right? So the guy who is doing the job, who is getting trained for us is that FW, right? The model for energy. Now, say I want to sample from this model, what should I do? Essentially, I need to get this Boltzmann expression, right? So I have the energy level, the energy model being trained, and then I put it in the Boltzmann formula, and I can compute the distribution, right? We talked in section 1 about this, that sampling a known distribution when it's very high dimensional is a very hard task, right? So I do know this, but for the moment, assume that we can do it, okay? I'm going to explain how we can do it later, approximately. But right now, even though I do know that you know that sampling is a very hard task to do, assume that you can do it, because we are actually a bit behind this. We actually have higher level of complexity right now. So assume that if I give you one known distribution, then you are able to sample from it by some trick, okay? The question is that if I give you energy model now, can you sample? So let's look at it together. Say I have trained the energy model, okay? So that f function has been trained. I just used maximum likelihood on one very big data. Now, if I want to sample this guy, let's look at the sampling process, how it's going to look like. So I'm going to start with the energy model, right? I have this guy trained. Now I have one particular sample x. I want to know what is the distribution of x. How can I do it? I'm going to give x to my energy model. I'm going to get the level of energy, right? Once I got the level of energy, I'm going to put it inside the Boltzmann formula, right? This means that after this guy, I'm going to compute the exponential function of this one, right? E to power minus the energy, right? Now that I computed this one, what should I do next to compute the distribution? Partition function, right? So I'm going to give these exponential into this partition function, and then I'm going to compute that partition function. If I have the partition function, then I have the exponential, the partition function. I divide them, I'm going to get the distribution, right? So this is the whole Boltzmann formula, correct? Now, this red box here, the partition function computation, what is the complexity of doing this? Assume that x is binary. Every element could be either 0 or 1, 2 cases. How many cases of x do I have in total? If I have a vector, a binary vector of size 2, how many cases I have? 4. Of size 3? No? 2 to the power 8, right? Of size d? 2 to the power d, right? Now, for every single dimension, if I have c different cases, or if I want to approximate it with c different cases, then I'm going to have, again, c to power d number of operations going on here, right? So this partition function that I want to compute is essentially, again, exponentially hard, right? So it's true that I have the energy. It's true that I can find the exponential, but I cannot find the partition function to normalize. So I can simply compute my distribution up to some normalization factor, but I cannot find it exactly, right? And this is the trouble, because even if I could make a kind of Gini model which can take the distribution and sample from it, I'm still unable to use that Gini because I'm not able to compute the distribution itself, right? So this is a big problem. So it is exponentially hard to directly or to compute essentially the distribution directly from the energy. This is impossible. Yeah? And you can think of the real data with huge D, right? One high resolution image. This is impossible, right? Okay. So you can guess that when this is the case for sampling, this is going to be the same thing for this training as well, right? Because probably somewhere in training, I again need to compute the partition function. And partition function is very hard to compute, right? So let's take a look at this guy here. Say I have a bunch of samples. So I have this data set. I have collected n different images inside that. And I want to train my energy-based model to on this data set. Okay? Now, what should I do if I want to do training? How can I train a model for generation? Nothing on this slide. Everything on your heart? Maximum likelihood, right? Always maximum likelihood. So I'm going to do maximum likelihood. ML is here, right? Maximum likelihood estimation. What does it mean? It means that I should take every single sample I have inside my data set. I compute the distribution at that point, right? Then that's going to be the likelihood of my model, right? Then I try to optimize it on the model parameters so that the likelihood is maximized, right? So let's write it together once again. So this is going to be the likelihood. So the likelihood, L, is essentially P, the model distribution, PW. This is the model distribution at the particular point xj, right? And then we are usually happy with log. So we're gonna keep log here. And then we add them up. We average it over the data set. We have done it a couple of times, right? So we're going to compute the average log likelihood, right? What is this PW here? Is the distribution of my model. How can I write it down in energy-based models? Boltzmann. Great. So I'm going to replace the Boltzmann expression, right? So I'm going to replace the Boltzmann expression. It's going to be e to power minus my energy model divided by the partition function. And we talked about this, that the partition function is not a function of x, but it is a function of the model, right? Because if I change weight, those exponentials are going to change. Their sum is going to change as well, right? And because of that, this partition function is going to change. So this is a function of my model parameters, but it's not a function of x, obviously, right? Because it's a normalization factor. Now, I have put this guy here. So can I open this logarithm? It's going to be log of the numerator minus log of the denominator, right? What is the log of numerator? Log of exponential function is the exponent itself, right? Assuming that the log is in the natural base, right? So log of exponential minus f is minus f itself, right? So it's going to come out of this exponential, I write it down here, minus log of the denominator, which is the partition function, right? Clear? So I need to average this guy over all samples that I have. The second term here, log of the partition function, does it depend on my sample? No. It does not depend on x, so whatever sample I put is going to be always the same, right? So now, if I compute 1 over n sum j, that log, when I average it over samples, it's going to remain the same. So it's going to come out, right? So I can simply write it down minus log. I keep it here. And then this averaging is going to be over my samples, right? So what you see here is that this log likelihood that I want to compute is essentially the log of my partition function minus the average energy at the points that I have, right? At the samples that I have. This is the log likelihood. Clear? And you can obviously see that it's hard to compute because, again, I need partition function, right? And this partition function I cannot get rid of because it depends on the parameter I'm going to optimize, right? It depends on the model parameters, W, right? Everybody's clear? Questions? No question? OK. I'm going to do I'm going to define one notation here, which we're going to use a lot through semester. And this is going to make life easier for us. So let's look at this guy. So this expression here, this is the second term here. You see, 1 over n, summation over all samples, my energy. So this expression, 1 over n summation over all samples of anything, this is the average of what is under summation, right? So it's like you compute your energy at all your samples and then you average them, right? Add them up, divide them by their number, right? We talked about it that this is one estimator of the expectation, right? Meaning that when n is very large, this expression is going to be exactly the expectation of f function, right? So you remember this, right? This is law of large number. The expectation of any function f of x is approximately 1 over n summation of fxj's, right? Any function I put here, if I average it over all samples taken IID from the same distribution, when n is very, very large, this is going to approximate very closely the original expectation. Everybody's clear? So what I'm going to do from now on, many times, I'm going to use this notation. And everybody's happy with this notation? So I put it expectation hat because this is not the exact expectation, right? So it's approximate of that. It's an estimate of that, right? But it's still, I write down in the index x distributed by p. Do you see why I write x distributed by p? Exactly, because x's, all those xj's that I have here are coming from distribution p, right? So I have sampled that distribution p. I got lots of samples. Now I'm averaging over it. I'm going to show it by approximately expectation of my function over that distribution. Everybody's happy with this notation? Questions? No question? And when you have such a notation, it simply means that in the ideal world, you're looking for the case where you can drop that hat. Yeah? So you don't want to estimate, you want the exact expectation. But you don't have it, of course. You need to use the estimate, right? Now that I'm doing this, so my expression, my log likelihood, is going to look like this, right? So look at this one once again here. So it was minus log of the partition minus that term. I show it by the average of energy, so I can write it down in this form. So this is E hat This is the one, the other term we computed. And this guy is log of the partition function, right? And I take out the minus. So when I want to train, what do I do with this function? I'm going to maximize it, right? So I can drop minus and instead minimize it, right? So typically the risk function that I want to minimize is minus this guy, right? So I'm going to get this e hat plus the log of the partition function, and I want to minimize it, meaning that I want to give it to one optimizer. It should be able to backpropagate over some network and compute the gradient of this risk function and update, right? But now, if I want to do this, can I do it here on this formula? Can I backpropagate over the first term? I can. Can I backpropagate over the second term? It's going to be exponentially hard, right? Because it's going to have exponentially large number of terms, right? And I need to backpropagate over all of them. Impossible, right? So again, if I want to do the training here, it's pretty much impossible because the objective function that I have and I want to minimize is exponentially hard to compute, right? So this guy, I can simply compute it based on my data set. So I have a bunch of samples from P inside my data set. I have access to my network. It is quite easy to evaluate my network. So I can compute this guy. But this one, it again needs exponentially large number of operations to be computed. This is essentially impossible for us. Questions? No question? Everybody's clear? What is the issue? Yes?
I have one question. Can you explain the XP notation again?
This one? Yeah. Which part you want exactly? Why x is distributed by p? Yeah. Because I assume that those xj's that I am averaging over here, they are all coming from the data distribution, right? So this is by this notation I simply mean that those samples I use are coming from distribution P, right?
Oh, yeah.
If I take it from another distribution, then this expectation is going to be different, right? So, and by distribution P, for instance, I simply mean like they are all MNIST images or they are all CFAR images, right? They are not, for example, ImageNet images, right? It depends on your data set. Yes? This one? Yeah, because partition function, if you remember, I'm going to show it in the next slides again. The partition function is summation of e to power minus energy over all possible cases, right? All possible cases of x. Now, x is an array, right? You can think of x to be, for instance, one vector of size d, right? And then when the vector is of size d, assuming every single entry has c different possible outcomes, then you're going to be c to power d possible vectors, right? And you need to consider all of them and do the summation. So it means you need exponentially a large number of summations. Yes?
Sorry, how do you compute the expectation?
This one?
Formula, like average in the data set?
This one?
Yeah.
Yeah, exactly. I do this, right?
Then why do you replace it with this expectation?
Yeah, because this is, first of all, going to simplify the notation. This is the only thing. But later, when I want to just generate some formula like this for this one. This is the reason. But if you read anything in the literature, many times you don't see this expression. You see only this one. And some people are lazy to distinguish between hat and without hat, so they even drop hat. They would say, OK, you are able to understand that if I don't have it itself, I can approximate it by a data set, right? Yeah. No worries. Questions? No question? Great. So if you got no question, then just let me wrap it up here for you for once. So sampling and training in the direct form, in the basic form, for energy-based models is quite hard because essentially you need to compute the partition function, right? You need to know the partition function to know what is the distribution. And this partition function is exponentially hard to be computed. And It's not a magic, right? When we talked about the sampling, I told you if you want to sample directly, you need to sort out all possible outcomes, right? And then compute the probability, and then you do the sampling, right? In the section 1, we did it that way, right? And now here, I am not making that table of all possible outcomes. I'm just computing one distribution, right? But again, the complexity is somehow hidden inside computation of the partition function, right? So when one problem is exponentially hard, you cannot change it to some polynomial without any loss, right? A hard problem is going to remain hard, right? It's not going to change. And I mean, mathematically, we did not expect that we're going to end up with a very simple solution, right? So that being said, now this might come to your mind that now we are actually in a bigger trouble, because before this, when we talked initially about training any model for distribution, we talked about this, that sampling itself is exponentially hard, right? But then when I wanted to explain this one, I told you, assume that you are able to do sampling. Now let's see whether we can do it or not, right? And the point was that you are one step behind. Actually, you are not even able to compute the distribution so that you do the sampling, right? So you might think that, okay, we are now in bigger trouble, so we have 2 levels of complexity. But the answer is actually interesting. The answer is that no, you're not. I mean, you're back at the same place. You are still having the trouble with sampling. Or in other words, if you are able to do the sampling, so the assumption that I told you, if I give you one distribution, or one, for instance, energy function, and you are able to do sampling from that distribution, then you are fine. Actually, all of these complexities that I talked about here are going to disappear. And you might wonder, how is it that possible? I'm going to show you very quickly. So everybody got the idea? The point that I want to mention now is that essentially everything going to break down, reduce to the problem of sampling one distribution, one big joint distribution. This is going to be your main task that you need to do. If you can do this, actually you can do the training without the need of computing the partition function. Okay? Might sound a bit weird, but I'm going to show you quickly. Any question? No question. Okay, so let's do it together. Let's put this assumption that I told you initially concretely here. So assume I have a genie, and this genie is able to sample the distribution. And to just keep it simple, I say that I'm going to give the energy function to it, and it is able to just generate samples from that energy function, right? So this genie has access to that bottom, right? I give you the energy model, it's going to press the bottom for me, and I see samples, right? Proportional to that, that energy model, right? The Boltzmann distribution of that energy model. So assume that we have access to this genie. Let's see what we can do with this genie. Okay. Well, say we want to do the training. If I want to do the training, I essentially need to minimize that risk function that I showed you. And if I want to minimize that risk function, I should be able to compute the gradient of that, right? That's the only thing that I need, right? I need to be able to compute the gradient, right? Okay, so let's compute the gradient. This is the term that I showed you, right? This is the risk function, expectation of the average energy, and this is the partition function, the hard thing to compute, right? Now, if I want to do the gradient, I'm going to just apply the gradient, right? So gradient of the partition, this risk function is gradient of the first term plus the gradient of the second term, right? Now, gradient of the first term, I can take that gradient inside expectation, right? So expectation is a linear operation. I can apply the gradient inside. So it means that I am going to write it down in this form, okay? No magic, right? Now, this term, can you compute this guy? I mean, forget about the expectation. Can you compute the gradient of this function? Yes, this is energy model, right? This is a neural network. And you can compute the gradient. What do? Backpropagation, right? So you can compute this guy by backpropagation. That's no problem. The problem is actually here, right? And we did know this, right? So let's look at this major problem, see how I can do the gradient of this logarithm without knowing the partition function, okay? And I'm going to expand this gradient of the logarithm. So I'm going to open it up. Gradient of logarithm of something. How can I write it down? What is the derivative of log x? 1 over x, right? So if I have log of one function, how can I write the derivative? Derivative of the function divided by the function itself, right? So I'm going to write it down this one. Gradient of the partition function divided by the partition function, right? Clear. Good. Now, what is the partition function? The partition function z is sum over all possible cases of the exponential function, right? This was the definition of partition function, right? Now, if I want to compute the gradient, I need to apply the gradient over all of these exponential functions, right? So gradient simply goes inside the summation, correct? Correct or not correct? Right? Okay. Now, gradient of the exponential function. How can I write that one down? E to power minus x. What is the derivative of this guy? Is minus e to power minus x, right? Now, if I have e to power minus f of x, what is the derivative? Just apply the chain rule. E to power minus f of x. If I want to compute the derivative of this guy, so right now you assume this is just a scalar function. What it would be? It's going to be derivative of this guy. It's minus e to power minus f of x. And then one other term I need to add, and that is f prime, right? The derivative of this guy. So it's going to be f prime of x, right? Now, if I do it in multidimensional case, I can simply write it down as the gradient of f, this is the guy inside the exponent, times e to power minus that guy. I have a minus also left here, right? Everybody's clear? Yeah? No magic, right? Okay, so now I have this guy. This is the derivative of z. I'm going to replace it here, right? Okay, so I'm going to write it down. The gradient of the logarithm, it was this gradient divided by z itself. So z does not depend on x. It can simply go inside the summation, right? So this other term that you see here is essentially the second line in the middle divided by z, right? Everybody's happy with that? Questions? Now, if you are happy with that, can you tell me whether you see anything inside this summation which you had seen before? Boltzmann equation, right? Do you see the Boltzmann equation? E to power minus f divided by z is Boltzmann, right? So this guy is the Boltzmann distribution, correct? So gradient of log of z equals to minus summation gradient of f times Boltzmann distribution, right? So let me write it down here. So gradient of the log is minus summation of gradient of f times Boltzmann distribution. What is this guy? What is this expression? Can I simplify it? Is there any specific definition that I can use to simplify this guy? If you have something which is a function of x, and you multiply it at every single possible x with this corresponding distribution, and you add it up, what are you computing? Expectation. Great, right? So you are computing expectation, right? So this guy is essentially expectation of that gradient function, but this time it's not over the data distribution, it's over what? The Boltzmann distribution, right? Your model, correct? Because the distribution showing up here is the Boltzmann distribution. Everybody's following? Yes? So this is expectation of the gradient of f. Can I take the gradient out? Yes, I can. I mean, it's a linear operation. Expectation and gradient, they always exchange, right? I mean, not always, but always when we have a well-defined function, right? So they are going to exchange. So I can simply take out that gradient and I can write it down in this way, right? Minus gradient of that expectation, right? So now, I told you that you have the genie who is able to sample from the distribution, right? If you have the genie which is able to sample from the distribution, can you compute that expectation? Or can you estimate it at least? Yes? You can do it, right? You can just ask Genie to give you enough samples, right? And once you have it, you just compute your function at those samples, you average them out, right? That is the estimator of the expectation you are looking for, right? So if I have access to the Genie who is able to sample from the Boltzmann distribution, then essentially I can approximate that expectation under the gradient, right? Because I could simply say that this expectation is approximately this, empirical average over the samples given by the Genie, right? Everybody's clear? Questions? So I promise you I'm going to disappear some elephant. You see this? The elephant was the partition function. I just disappeared it, all right? So, questions? Everybody's following, right? So it was not it sounds interesting and a bit advanced, but it was not really a big math, right? So, moral of the story, so I can compute this gradient if I am able to approximate this, or I am able to sample from the Boltzmann distribution, right? And the gradient of my, partition function, log partition function, is going to be computed in this form, right? Now, if I take this guy back and put it inside the risk function that we initially started with, so my risk function, the gradient of the risk function, is going to be the first gradient, which we talked about before, minus gradient of the expectation of the same function, this time over the model distribution, right? So you have the same energy function. You're once averaging it over the data distribution. You once average it over the Boltzmann distribution, and then you just subtract them. You find the divergence between these two. This is going to be the thing you need to minimize, or you need to compute the gradient in order to train your energy model, right? Everybody's cool, right? Okay, so moral of the story, if you want to do maximum likelihood estimation here, you essentially need to compute this guy, right? This guy is not hard to compute. The first term is essentially the term which I can compute it by the data samples. And the second term, I can take my Genie to do that for me, right? So now I can do it using my Genie. So this one, I can simply do it by sampling from the data distribution. And this one is simply done by sampling from the model distribution, right? Which we don't know how we can do it, but we can rely on the Genie right now. We're going to see it in a couple of slides. Questions? No question? Everybody's happy with what we did here? Yes?
Actually, Professor, I was wondering, is the divergence metric?
Yeah, it's a kind of divergence metric because you get the same function and you average it over two different distributions, right? And then you compute their difference. But it's not divergence metric in the sense I told you initially. So not mathematically defined divergence, because it could get negative, right?
Oh, so that's like, we have the expectation here and we're subtracting, and that's
yes,
divergence,
yes.
That, like I was thinking of the KL.
Yes, yes, yeah. Yeah. But I mean, essentially, if you put it really to be this guy, if you put it really to be expectation, this guy to be expectation, so they are not approximate expectation, then it cannot be negative, because essentially, or it could always be positive with a constant, because essentially what you're doing here is maximum likelihood, and you are minimizing KL divergence. So this is somehow proportional to your KL divergence. It should either be, it's always more than something. Yeah, you can always say that, but I don't want to complicate it here. Okay? So the moral of the story is that you are somehow computing a sort of divergence between the distribution you have as the data distribution and the distribution explained by your energy model. Questions? No question? So one interesting thing inside this expression is the kind of trade-off you can see when you want to train the model. So it's going to give a very intuitive trade-off we are trying to do in order to train our energy-based model. So what is the first term here, this expectation? This is expectation of the energy function. This is the energy level of my data, right? And I'm doing it on my data distribution. It means that I take samples from data distribution and I compute the energy, right? Now, if I want to minimize this divergence, this distance, this difference, if I want to minimize it, what should I do to these energies? I should make them small, right? So it means that I need to make my energy function to be small at my data samples, right? What about the other one? Should I make the energy also small at the model? No, I need to just push it up, right? I need to make it large. So this is a very interesting observation we see here. We need to reduce energy at data samples because we know data samples are good guys, right? And when data samples are good guys, then energy is very low because low energy means high likelihood, right? Remember, e to the power minus energy is the likelihood, right? So low energy is going to make us high likelihood, right? But we need to increase the energy at the model samples. And you might guess why. Because model has not been trained yet, right? It's giving me bad samples, right? So I need to just make the energy high, meaning the likelihood that those samples are low, right? And by doing it iteratively, I'm going to gradually converge to the point where my model is just approximating the data distribution. Everybody's cool? So if you got no question on that, then the moral of the story is that I can simply do training if I am able to do the sampling. So I hope I could make this point clear for you that all of this computation of the partition function at the end of the day is going to reduce to our original problem. And the original problem is that we are unable to sample a distribution, a big distribution, because it's exponentially hard, right? If I am able to do that, at least approximately, then the whole problem is gone, right? So as long as I have the sampling genie, which is able to sample my distribution simply by knowing the energy, then I am essentially able to train my model. And training is quite easy, right? How can I train this model? Say I have a data set. Then I'm going to go over this data set for multiple epochs. And in every epoch, I'm going to take a batch of samples, for instance, and then these are all coming from the data distribution. Then I use my genie to generate the same number of samples from the model, right? So I'm going to sample the Boltzmann distribution using my genie with the same number of samples, right? And now I have these samples. I basically go inside the loop and I compute the backpropagate over my energy model, once using my data sample, once using my model sample, right? And then I subtract them. This is going to be my gradient. So the gradient that I need is subtraction of these two gradients, and update my model W using that gradient, right? And I keep on doing this till my model converges, right? Everybody's clear? So having the sampling genie, I am over with the whole problem. The question is how I can have a sampling genie, right? So, questions? No question? So the sampling genie is simply doing the training for me. Also, it's going to do the sampling for me, right? Because it's already sampling, right? So if I want to have a new sample, once I have trained my model, I have the train energy, right? And I'm going to give that train energy model to my genie. It's going to give me one sample, right? The problem solved, right? So I just need to make the sampling genie. That's it.